Good evening all. How y'all doing out there? Let's get started on the explanation of the Hall Effect Encoder Simulator. Now I use the PIC16F877A-I/P. You can use any microcontroller you want, but I like this IC right here. And if you do use your own IC, you'd have to reinvent the code. Okay, so here's the Phoenix connector over here. And pin 1 and 2 are Z and Z bar. The bubble of the AM26LS31CN, the bubble indicates it's inverted from pin 2. The B channel, 6 non-inverted, 5 inverted. So you'd have B and B bar. The A channel, 10 non-inverted output, 11 to pin 6 inverted output. So you would have A and A bar. Now, this is our data bus right here. And we'll go down and look at the open collector A, B, and Z channels here in just a little bit. We're looking at the differential output right here. The AM26LS31CN, I'm going to get sidetracked from the data bus here, sorry about that. But you can open up many actual encoders and you will see this IC right here inside that encoder. And that's why I chose to use it. Very familiar. So the data bus, port B is going to the input of the A channel, RB0, port B0. Port B1 is the output for the B channel, and port B2 is the output for the Z pulse. Now up here I connected it anyways, but it's not used. I might find use for that in the future, but right now it's no connection. Now let's go and look at the Hall effect. And you'll see here in just a little bit the reason we used an SN74HCT374N. We'll get back to this page in just a little bit, but we're going to look at the Hall effect output. So remember A, B, and C on the 16F877 data bus. I'm calling this the data bus. Here's A, B, and C, and again Z is not used. This is a different 74HCT374. So we had the one for the encoder, incremental encoder output. Now this one is for the Hall effect. And certain drives, believe it or not, they'll use a differential output. So I included that in the Hall effect encoder simulator. But here's Hall effect 1 on pin 1 and pin 2. And so this is not inverted. Here's our bubble. This is inverted. So this would be Hall effect 1 and Hall effect 1 bar. And on 6 and 5 output right here, going to 3 and 4, we have Hall effect 2. So pin 3 is Hall effect, pin 4 is Hall effect bubble. On pin 5 from pin 10 and 6 from pin 11, we have Hall effect 3 and Hall effect 3 bubble. So you can see that these inputs here are shared. So I have to select from the code, from the microcontroller, where that data from these inputs go, either to the incremental connector or the Hall effect connector. So here is our incremental side, and here's our Hall effect side. And that is for the differential output. So we can clock the data either here to this connector, this is another Phoenix connector, or we can clock the data to this connector. So depending on how the Hall effect encoder simulator is programmed, determines where the pattern goes. Let's go look at the open collector output for the incremental encoder side right here. Before we get started, let me show you the enables for the AM26LS31CM. On pin 4, there's enable, and an enable bar on pin 12. Now I'll tie this one up to 5 volts, and this one here to 12 volts. And that will enable the outputs of that IC. Now here on this data bus, I've labeled RB4, port B4, port B5, port B6, and port B7, F, E, and D, and Y. And up here Y is not used, but I connected port B7 to the 74 HCT374 just in case I wanted to use this output sometime in the future. So this is common to the data bus back here on the Hall effect side. Let me show you that real quick. So these points right here and these points right here are connected together. Now for open collector, there are some times, and you'll see this in an actual encoder, you'll see that the outputs are actually open collector, NPN or PNP, normally NPN outputs. And I used a ULN 2003 to open collector drive the outputs here on the Phoenix connector, pin 12. Channel A is connected to the output of this open collector, ULN 2003. 11 is channel B, and that's connected to pin 12. Channel Z, the Z channel on pin 10, is connected to 13. And they're connected back to the ULN 2003. His inputs are connected back here to the 74 HCT374. So the encoder output A, B, and Z have these connections right here. Now look here, we have 10 kilo ohm pull-ups, and that's going to pin 9. This is our pull-up voltage input. So if your drive required pull-up resistors, your drive can supply the voltage to the pull-up resistors on the Phoenix connector pin 9. And up here is the ground of the logic. Now let's go look at the Hall effect side. Let's move this out of the way. It's identical, except instead of incremental encoder patterns sent to the Phoenix connector, we have Hall effect patterns sent to the Phoenix connector. Hall effect 1 on 10, Hall effect 2 on 11, Hall effect 3 on 12. Now this is a different Phoenix connector. The incremental encoder outputs are on Phoenix connector P6. The Hall effect outputs are on Phoenix connector P5. Also, the AM26LS31 and the 74 HCT374 are separate ICs between the encoder outputs and the Hall effect outputs. Now on the 29th of September of 2016, I added a 7414 between the output of the 74HCT374 and the input of the ULN 2003. And I did that because on the Z pulse, without that inversion, prior to reaching the input of the ULN 2003, the output was always high. Well, that's not how I wanted the output to be. I wanted it to be mostly low, and for the brief pulse at pin 10, the Z channel output, I wanted it to be mostly low, and then when we had a Z pulse occurrence, it would go high and then low again. So I inverted it right here. And just to keep in step with everything, we had these three channels right here inverted with a 7414. I'll show you that when we get to that modification page. And I also did it with these Hall effects, whereas just keeping in step so that everything was equal, so everything was the same. I modified this point right here by adding the 7414 as well as this point right here, but mainly because I wanted the Z channel to go low to high on this open collector output of the ULN 2003. Here are the modifications I was just talking about. I used a 74HCT114, and that inverted the output of the 74HCT374 before it reached the input of the ULN 2003. And down here you can see what it looked like before the inversion. Before the inversion, the C channel was mostly high, then went low. This is on the open collector side. And after the inversion of the 74HCT14N, it looked like this: low to high to low. And that's what you want with your pulse right there. I did the same on the Hall effect side, just so we would have the same circuitry. In future troubleshooting, that makes it a little bit easier when everything's pretty much the same. Here we are again. Day 2 of the explanation of the Hall effect encoder simulator hardware. It's going to be a long couple of series of videos. I printed off the code that makes this thing get up and go. It's 140 some odd pages in length. Oh Lordy God, what's that going to look like? Now the question presented to us is, how do we apply that data bus, the PIC16F877A I/P data bus, to the output, either the P5 connector or the P6 connector, the Hall effect output or the incremental output. So previously we saw that we could apply a Hall effect pattern or an incremental encoder pattern to the data bus, the inputs of these two ICs right here. So how do we determine whether we're going to apply Hall effect pattern data to the output or incremental encoder data pattern to the output? And we do that with port D1 and port D0 providing a clock input to either IC2 or IC3. Here on pin 11, we have the clock pulse input on both these ICs. IC2 being the Hall effect output, and IC3 being the incremental encoder output. When we apply a clock pulse on pin 11, a low to high to low, the data on the input of this IC is latched into the output. It's an octal D flip-flop. And same down here on IC3, the incremental encoder output. When we go from low to high to low, that incremental encoder pattern is latched to the output. Now here pin 1, we've got those tied to logic ground on both ICs. As an aside, an explanation of this output enable. When the output enable is high, we have 5 volts on pin 1, the output is in tri-state, high impedance output. Let's talk about the controls and switches that set up how the Hall effect encoder simulator operates, how it will perform as a feedback device simulating your motor. When you first power up this tester, this LED right here in switch number 1 will be blinking fast. That's this LED right here blinking fast. And that's when you want to set up your pulses per revolution. So for instance, if you wanted to set your feedback simulation for that encoder output to 50 pulses per revolution, you would push the A button. Here's A, B, C, D, E. You'd push and hold that button and then push the number 1 switch. And that would set that output to 50 pulses per revolution. By pulses per revolution, what I mean is that your first occurrence of the home pulse, and then you would have 50 pulses until the next occurrence of that same home pulse. So once you push the A switch, you push the number 1 switch, number 2 will start blinking. This LED right here inside that switch, there's an LED here and an LED here, and this LED on the number 2 switch would be blinking fast. And that will, oh, let me go back. If you want to set the output to the default, which I set to 1000 pulses per revolution, you just push that number 1 switch and the output will default to 1000 pulses per revolution. And so now we're over here on switch number 2 blinking fast. That LED is blinking fast. That's a visual indication to us as to where we are in the programming process of setting this tester up. So now if we want, let's say we want incremental encoder and Hall effect to be processed to the output, the open collector output ULN 2003. We would push the B button right here and then push the number 2 switch up here. And at that point we'd be over here with the number 1 switch again, but blinking slow instead of fast. Now if you want to default to incremental encoder and Hall effect, going to the AM26 LS31, the differential output, you would just push the number 2 switch right there and it will default to that value. So now we're over here back to this switch, but the LED is blinking slow. And we want to set the leading edge of the A pulse. That's where the Z pulse will trigger, on the leading edge of the A pulse. So we push the B button again, and then we push the number 2 button. And that will set the trigger of the Z pulse to fire on the leading edge of the A pulse. But the default, if you want the default, just push that button right there and it will be the leading edge of the B pulse. Will be the default when that Z pulse occurs. So the width of the D pulse, now we're on switch number 2 right here, and the LED is blinking slowly. And let's say we wanted just a very brief Z pulse, and it would look like this: high, low, low, low. We would push the A button and then push the number 2 switch, and we're fully programmed. But if you want the default, which is mostly high, you would just push the number 2 button right here. Now that's how you set it up. But let's look at the switches and the buttons now. The actual circuitry. Here are switches number 1 and switches number 2. These are the switches with the blinking LED internal to that switch. So we have a 10 kilo ohm pull up here and a 10 kilo ohm pull up here, pulled up to 5 volts. And so at that point right here, RD2, port D2, and port A3, that's 21 and 5 on the PIC 16 F877-I/P. This point right here would be a logic 1, plus 5 volts. When I push switch 1, this point right here would be pulled to ground, and we would have logic 0 right there and a logic 1 right there. And release this switch, this goes back to logic 1. We push switch 2, and now pin 5, port A3, would go logic low through the switch. Here are the switch 1 and switch 2 LEDs. These are the LEDs inside those 2 switches. And we have 220 ohm current limiting resistor connected to 5 volts. That's tied to the anode of the LED. The cathode of the LED for switch 1 goes to port A1 on pin 3 of the microcontroller. Now the cathode of the LED for switch 2 goes to port A2, pin 4 of the microcontroller. Now when port A1 is high or port A2 is high, that switch will be off because we will have no current flow through the LED to that port. Now when port A1 or port A2 is low, that will tie the cathodes of the LEDs to ground, logic 0. So if we have logic 1 here, the LED is turned off. And if we have a logic 0 here, the LED is turned on. Now this connector right here, this is how we connect our switchboard and LED board to the microcontroller. And up here, you can use any connector that you want. I use a ribbon connector. But we have 5 volts from the power supply over here that comes over here and makes the pull-up resistances voltage for these points right here. And we have ground from the power supply over to ground of the switches. Now, when I first started thinking about making this tester, I was thinking about using an LCD, and I was going to call this the up button, the down button, the left button, the right button, and the enter button. And you would be able to scroll up and down through menus, left and right, to select different things, and then press enter when you wanted to complete your programming task. But after I started working, I said, well, you know what, that's just extra hardware and extra code to send display data to the LCD. So I said, we don't need that. We're just like gonna simulate a feedback device, a motor feedback device. I don't need an LCD. This don't have to be that fancy. So I never pursued that. But in the code, I call it up and down and left and right and enter. But on, as you saw in the, just a little bit ago, it's actually A, B, C, D, and E. So when you see the code and you see the up button in the code, I named it up, it's actually the A. So here we go. For the A button, when it is open, we have a 10K pull-up resistor pulled up to 5 volts, and that applies a logic 1 to port D bit 7 on pin 30 of that microcontroller. When we push button A, it ties port D7 bit 7 to ground, and we would have a logic low there. The same occurs with the B button. We have logic 1 on port D6, push the button, ties that point to ground, and we have a logic 0 on port D6. Same for button C. When button C is not pressed, port D5 on pin 28. This is 30, 29, 28. On pin 28, port D5 is pulled up to 5 volts, so we'd have a logic 1 right there. Push that button, it ties port D5 to ground, and we have a logic 0. Now these are inputs. On port D4, that's pulled up to 5 volts through this 10 kilo ohm resistor, and we have a logic 1 there. When we push button D, that ties this point to ground, and we have a logic 0 on port D4. On port D3, we have a 10 kilo ohm pull up again to plus 5 volts DC, and we have a logic 1 right there. When we push button E, this point right here goes low, and we have a logic 0 right there. So we saw how to program, how to set up the pulses per revolution, whether it's going to be Hall effect or encoder output on P5 or P6, P5 being the Hall effect, P6 being the encoder output, and whether it's going to be open collector or differential output, and where the Z pulse for the encoder output, at what point that that fires, whether leading edge of A, leading edge of B, trailing edge of A, trailing edge of B. And we saw the home pulse width that we could change, either very narrow or very wide. There you go. We got a few more pages to explain, but we'll save that for tomorrow. Have a good night, all. We'll see you tomorrow. Oh, well, here we are. What is this, day 3 on this little project right here? So, I'm an idiot. And in the last video, where you were able to take screenshots of the schematic diagrams that I got drawn out for this tester, I had the power supply section right here. Here's on the green connector we have plus VN. On the V terminal going to an L78SO5CN. That makes the 5 volts for the logic, and ground on the G terminal. And then we have over here 5 volts and ground. And here's where things got a little confusing. I have pull-up resistors on the open collector outputs of the ULN 2003. My original intent was to use plus VN to supply the voltage to the plus terminal, the pull-up resistors of that ULN 2003. But in the end, that's not the way it worked out, because I thought to myself, I should let the drive determine the voltage of those pull-up resistors, because sometimes the drive will put out 15 volts, sometimes 25 volts, sometimes 5 volts, and I shouldn't be able to determine the pull-up resistor. So ignore all of this. Come on, ignore it. This is not the way the circuit is. I'm trying to cover this all up. This is not the way the circuit is. That's no longer there. P5 pin 9 and P6 pin 9 are connected to the pull-up resistors of the ULN 2003. Now, sometimes you don't need a pull-up resistor, at which time you don't connect to pin 9 of the P5 connector or P6 connector. So I apologize. Don't connect plus VN to pin 7 of the P5 or P6 connector. So as a quick review, here's the Hall effect output on the P5 Phoenix connector. And we can see here that pin 9 is the pull-up resistors for the open collector of these 3 ULN 2003A. And pin 7 is no connection. And on the P6 connector, let's move this out of the way. Here's the encoder output. And the same circuitry, pin 9, not pin 7, pin 9 is the 10 kilo ohm pull-up resistors for these 3 open collector ULN 2003A. Pin 7 again, no connection. I apologize. I hope I didn't create no trouble for y'all. But this is the circuit. Here, us humans require a visual indication so that we know where we stand in life. And so this came some years after I put this circuit together. I would program the outputs, either open collector Hall effect output, differential Hall effect output, incremental encoder open collector output, or incremental encoder differential output. And after I had the circuit set up, the tester set up to run, I wouldn't know how it was programmed because I couldn't see. So what I ended up doing was I added these LEDs right here. And the LEDs tell us how that circuit is programmed. So many times after the fact, you add circuitry to help us navigate through how things are set up. So when this LED right here is illuminated, we're your open collector Hall effect output. And so what we do is we apply a high on pin 26, that's port C bit 7 to this 7406. This is a open collector inverter, and that pulls the cathode of this LED to ground so that current flows through this 220 ohm current limiting resistor from 5 volts through the anode cathode junction to ground inside that 7406, illuminating that IC. The same down here on port C bit 6, that turns on this LED right here, which indicates to us that we would be differential output on the Hall effect pattern. Port C bit 5 turns this LED on, where we would be open collector output on the incremental encoder pattern. And RC4 on pin 23, that turns on as well as turns off this differential output in incremental encoder pattern. Let's see what we got next. These two LEDs tell us whether our Hall effect or encoder pattern is running clockwise or counterclockwise. If we're running clockwise, port E bit 2 will turn on this LED. And if we are running counterclockwise, port E bit 1 will turn on this LED right here. Here are the control inputs to make this thing get up and go. We have start and stop. Now, I wished, but I just didn't do it, but I wished I used optocoupler inputs for start and stop and clockwise, counterclockwise. I didn't use optocoupler inputs because I'm generally safe with not applying a voltage greater than required for this input. These inputs are 0 to 5 volts on this microcontroller. If you apply a voltage greater than 0 to 5 volts, it's very, very, no, I don't say very, very, you're going to destroy that input. I'm talking about very, very possibility that you're going to destroy that input. You will destroy that input. And normally it's safer to install some kind of voltage level shift so that you protect that input. And that's done with an optocoupler, but I fudged on the inputs because I knew I wasn't going to do that. If you're worried about damaging this input, put you an optocoupler between here and there. But remember the inversion, because an optocoupler will invert the input from the opposite state of what you wish. So what I'm saying is that here we have 5 volts applied. This is when this circuitry is open. You have 5 volts applied to port C0 through this 10 kilo ohm pull-up resistor pulled up to 5 volts, so you have a logic 1 right there. If you had an optocoupler, it would be opposite. So the output of the optocoupler, when 5 volts is applied to the anode and cathode, or I'm sorry, to the anode, that optocoupler would be turned on, so you'd have 5 volts on the input, but 0 volts on the output, because that photo transistor would be turned on, pulling pin 15 to ground. Whew! Okay, so remember, if you do add an optocoupler, you're going to have some inversion. Now, that's the start-stop circuitry without an optocoupler. So to start, we pull pin 1 to low, pin 2 ground, and that applies a logic 0 to port C0. And that output, that Hall effect encoder output, will be enabled. It will start to run. It will start to rotate that simulated encoder or that simulated Hall effect, or both. And with this input open, we have a logic 1 right here. That output would stop. Clockwise and counterclockwise. Here on port C bit 1, when we have 3 to 4 open, we have a logic 1 on port C bit 1. And that output will run clockwise. And what we mean is that in clockwise rotation, the A channel output leads the B channel output. And when we close 3 to 4, we have a logic 0 on port C bit 1. And now the A channel lags the B channel. B channel leads the A channel on the incremental encoder output. Here we have an analog input, bit 0, and I have a potentiometer from the wings of the potentiometer connected to pin 1 of this connector, the ground connected to the other wing of the potentiometer, and the wiper connected to pin 2, and that goes to analog bit 0. Now I added a security key, and this was so if I left this thing laying around, which I do very often, that if I open this jumper right here to port E bit 0, then we have a high applied to port E bit 0, and that puts the initialization, I'll show you this in the code, that puts, after everything is initialized, and it puts it into an endless loop. We never get to the main structure of the program. The program does not run if this jumper is not installed. When I install the jumper, port E bit 0 is connected to ground, and that allows that program to continue on into the main function of the program. That keeps you from stealing your hardware and running off with it and using it. Well, what are we doing here? Anyways, I wanted to give this to you so that you could enjoy your life. You could use this tester to help you succeed in your troubleshooting abilities of different types of servo drives. You have to give back to society. You have to give back to society, and this world's given me a lot of opportunities to succeed and to fail. And I'm trying to give back what I can, if I can. Now, I do have a problem. The code that gets this microcontroller get up and going with this tester, PIC16F877-I/P. The code is 140 pages. It's greater than 140 pages, and I don't know how I'm going to put that up. Do y'all, and I'm internet illiterate, I can get around and look at stuff and whatnot, but if you know of a place where I could drop the actual code onto the internet, maybe a free website, library, or whatever, I don't know what you call it, but if you know of a place where I could put the actual code, the ones and zeros, where you could go up there and download it, I could save you a lot of trouble. That's a lot of typing. We're talking 10 years into this thing, from my aspect. From the time that I had the idea to the time it was fully completed. I don't want you to have to type in all that. That would take a good month or two of y'all typing. So if you know of a place where I could upload my program, and y'all could download it, that would be really nice. If y'all let me know in the comments. I don't want you to have to struggle through this this process right here. Okay. Now just remember, let me get this back up here. This is incorrect. This is not correct. The pull-ups are at pin 9 of the P5 and the P6 connector. The Hall effect output and the incremental output for the open collector side ULN 2003A. Ning Jango! My refrigerator Ning Jango just woke up. Oh, I'm trying to think of what else I can say. Folks, you've been very, very supportive of my channel, coming over and checking things out, and I hope that I've helped you out. If you can, help your neighbor out. We're always struggling. We're always trying to get through. Sometimes we do, and sometimes we don't. Well, I'm getting long-winded. Thank you very much. And I think in the next video, we're going to look at how to program, how to install, how to take that hex file and install it into a microcontroller. I think that would be a good thing to do, because that's going to be the next step after you get your code put together for this tester. We'll see you in the next one. Have a good night.